Welcome back everyone to another episode of the Reading Club, and in today's episode we will continue covering Presolve Reductions in mixed integer programming. Okay, so in the previous parts we covered a few things, right? So we covered Presolve rules that were basically about that were using one constraint at a time and one variable at a time as well. And in today's video we will cover pre-solved rules which use multiple constraints at a time. Okay, so if you haven't watched the previous parts, I don't think most of them are necessary for this part, but I think at least I'll recommend watching the first part so that you are familiar with the notations. So without further ado, let's get started. Okay, so the very first preprocessor we are going to discuss when we are looking at multiple constraints at a time is removing the redundant constraints. Okay, so we discussed this removing redundant constraints when we are looking at one constraint at a time, right? So if you recall that we have this kind of a constraint arx is less than equal to br, right? If we have this kind of a constraint, and if we find out the supremum, that is the maximum value that this part can take, if that is already smaller than br, then that constraint is redundant, right? So that's what we discussed. But now we are going to discuss this in slightly more detail. Okay, so first of all, what exactly do we mean by redundant constraint? So constraint is redundant if we can remove that constraint from the set of our constraints and our set of solutions remains the same, right? So let's say we have this is our set of feasible solutions of our mixed integer program, right? And if I, let's say, remove a particular constraint, even if its supremum may not be less than equal to br, in that case also, if I just remove it and none of these points are removed or no other points are being added, in that case we can say that this particular constraint is redundant. Okay, and we want to detect this kind of redundant constraints, and it is actually already an NP complete problem. Okay, so that is detecting, or rather deciding if a constraint is redundant. Right, so how is it NP complete? It's a very nice proof that they gave in the paper. It's this thing that if I have, let's say, a mixed integer program, right? Let's write one ax, let's just for now write with less than equal to b, and some bounds for x, right? And why is detecting redundancy and NP complete? Because I can just simply add this kind of a constraint, 0 less than equal to -1, and this constraint is basically making this MIP infeasible. So if this constraint is only redundant if the existing MIP, like this part, is already infeasible, right? And we all know that detecting whether a given mixed integer program is infeasible or not. Okay, this is a linear program, but we can say that some x are also integers, right? Not I, let's say z. Okay, xi is integer for I in I, capital I. Okay, so this is a mixed integer program, and deciding whether a mixed integer program is infeasible or not is already NP complete. And this is how we can say that calling some constraint, whether it is redundant or not, it is already a very hard problem. Okay, but first of all, we are not really going to talk about redundancy in terms of MIPS. Why? Because sometimes there can be constraints which are not really needed for not really changing anything from the MIP solution set, but they are basically making the LP relaxation a little bit stronger, right? So that's why if you just simply remove those constraints, then it will take a long time for us to finish the branch and bound process. So that's a bad idea, and this is why basically we add cuts to a mixed integer program, right? So cuts are basically all redundant constraints because they are not really changing the solution sets, but they are just helping us with making stronger LP relaxations. Okay, and so that's why that's one of the reasons why we don't really want to talk about redundancy in terms of mixed integer program. But what we will look at is redundancy in terms of LP relaxation, right? So this is from now on, this, let's say we are only considering the LP relaxation, we are not really considering this part. Okay, and we will call a constraint redundant if the solution set of this LP relaxation is not changing even if we remove that constraint, right? And that part is not really NP complete. Okay, because first of all, solving linear program itself we can do it basically in polynomial time, so nothing really is hitting this NP kind of spaces. But if, let's say, how exactly we can do that, right? So let's say if we have this kind of a constraint, right, and if we want to check whether this constraint is redundant or not, then what we can do is we can basically have an objective like this where we are maximizing AR dot X, basically the left hand side part of this constraint, and subject to all the other constraint. Okay, all of this constraint except for this one, right? And we solve this linear program, and we get our value here, Z star, let's say, right? And if this value is already smaller or equal to BR, then we know that this constraint is redundant. Okay, so this is like previously we talked about we basically only measured the supremum, but not all constraints will reach their supremum in their LP relaxation solutions, right? So because there are other constraints also present, so this is like slightly more involved. Even if sometimes the supremum is bigger than BR, this Z star value can be smaller or equal to BR. That means we can safely remove this constraint from the LP relaxation. Okay, but this still is it is not NP complete, it is not taking exponential time, but it's still super expensive. Why? Because we have to solve a linear program to detect that, right? So this is still expensive. So Gurobi does that, like basically triggers this kind of routines, like solve entire linear program for calling some constraint, detecting redundancy, right? So but not always, right? So they do it on some very special cases. Okay, so not always. And so that's the idea. That's like still one part. There are other parts. Okay, so this is for general type of constraints, right? So we don't really have any assumptions about the coefficients or the right hand side or anything, or even the types of variable or anything at all. And that's why basically we have to solve an LP. But if we assume some kind of structure on these constraints, then there are other procedures which we can use to detect redundancy. Okay, so let's see some of them, right? So first of all, we can say that the parallel rows are basically redundant, right? So if the right hand sides are same, or rather not necessarily same, but let's say a scaled version of this constraint, if we already have something, some scaled version of this constraint inside this, that means that if we simply just remove this, it doesn't really matter. So parallel rows, we'll discuss that in some time, not right now, but that's one of the way to detect redundancies, and that's also something that Gurobi does. Okay, so there is another thing which is called special type of factorization, right? So this kind of a matrix, right, we can basically, there is a special type of factorization. It's called let me erase all of this first. Okay, so it is called rank revealing. Rank revealing LU factorization. Okay, so if we do that, so this was by Miranian and Gu, and those people basically did that, and eventually, like if you do this kind of matrix factorization of our constraint matrix A, then all the redundant rows will be basically converted into 0 equal to 0 type of situation, right? So this equation they will be converted into, and if we get for some of those rows, if we get this in our factorization, that means they are redundant and we can remove them. But it turns out that this is still not really very helpful. It is actually kind of making things worse. So they're basically able to detect redundant rows, but this process is slightly it's not super expensive, but like at least not as expensive as solving complete linear program, because this is just one factorization. But the problem is that sometimes when we remove redundant rows, it actually increases the node count, and that is kind of surprising. Increases node count, right? So how is that? Why is that happening? So by default, when we remove some redundant rows, we expect that our branch and bound tree, right, this will not get affected at all. But apparently sometimes it is actually increasing the node count when we remove redundant rows, and the reason for that is that this redundant rows, they act as base constraints for generating other cuts. Okay, and these cuts basically help us reduce the nodes from our branch and bound tree. So if we sometimes remove this so-called redundant rows, then we won't be able to generate these cuts, which is why the nodes, maybe number of nodes can increase, right? So that's one of the reasons why it hurts sometimes. But in general, it should basically help when we basically remove redundant constraint. We expect LP to get smaller, the linear program LP relaxation. It should get smaller, and the exploration part of this branch and bound tree should be faster, and yeah, that's why it is supposed to help. Okay, so that's one part. There is a special type of structure also, right? So we talked about LU factorization, right? And we talked about solving LPs. And so there is one more type of constraint, which are called click constraints, right? So all the variables are binary and coefficients are 1. Binary variables and coefficients are 1. So we can say that sometimes some click constraints are redundant, right? So for example, if we have that x1 plus x2 plus x3 is less than or equal to 1. So this is one click constraint. Only one of these three variable can be equal to 1. So all of these are binary variables. And if we have one more constraint, x1 plus x2 plus x3 plus x4 is less than or equal to 1, that means that only one of these four variables can be equal to 1, right? So this constraint is a subset of this constraint, right? So this constraint is redundant, and we can basically detect that, and that is also a kind of slightly faster way of the clicks are maintained in click tables, so it is not really we have to compare each pair of rows. But yeah, so we can basically detect them, and even this part is not very helpful, right? So this part is also disabled, this part is also disabled, all of this is basically disabled, right? And the last part which I'm going to talk about, which is also disabled, right? So basically nothing really is enabled here, only this LP part is sometimes used, and single constraint redundant row detection is used, and parallel row detections are used, which we'll discuss it in some time. But yeah, let's talk about something else that is also disabled by default in Gurobi, right? So let's say we have this kind of a constraint, right? What's it called? It's called inequality subsumption. Okay, it's kind of hard to pronounce. Anyway, so the inequality is, let's say, something like this: ax is less than or equal to b, and in our MIP we also have, let's say, another inequality, ax plus, let's say, dy, right? And this can be less than or equal to or equal to b, not b, right? So let's call this b prime. Okay, so sometimes this constraint is redundant if we have this constraint present. When? So that kind of depends on what is the maximum value, or what is the smallest value this part can take, right? So what is that? That is infimum of dy. right, infimum of dy, and if that part is already greater or equal to b prime minus b, right, so that basically means that ax has to be less than equal to b. That is implied because of this, right? So if this happens, then this constraint is completely dominated by this one, and that's why this is redundant. Okay, and on the other hand, if we have only less than equal to here, not equality, right, only less than equal to here, and we measure the supremum of dy, right, and if this part, the supremum of dy is less than equal to b prime minus b, right, so the largest value that this dy can take is less than equal to b prime minus b, then this constraint is not redundant, but it basically implies this constraint, right? So if you can basically just try to put these numbers. Ax is already less than equal to b, so what the dy should be, based on this supremum and everything, rest of the part is kind of already followed, is already satisfied by this constraint, right? So in that case this constraint is redundant, and that's how we can basically detect some redundancy, and this kind of is already super hard, right? So we have to basically compare some pairs of constraints, not really pairs of constraints, we have to figure it out whether we have a superset of this LHS somewhere in our MIP, and we can basically compute this kind of infimum supremums when needed, right? Even this part is also disabled. Okay, so basically nothing really is enabled in terms of redundancy detection in Gurobi, except for this LP parallel row and single constraint redundancy detection. Okay, so now we are going to talk about parallel rows. Okay, so we have two rows, row number Q and row number R. Okay, so we have AQ and we have AR. Okay, and we have, for the rest of this discussion, we will have AQ equal to S times AR. Okay, so these are basically the coefficients of the qth row, this is rth row, right? And each coefficient is basically like just multiplied, like is a scaled version of the other corresponding coefficients. Okay, so this is what we are going to talk about now, right? So first of all, we have constraints, right? So we have also BQ and BR, right? And there are basically a lot of things which we can discuss, right? So first of all, the easiest thing is like if both of them are equality constraints. Okay, so in this case it is kind of super obvious that this BQ also has to be S times BR, and if that is the case, then we can basically discard this constraint, one of this constraint, and the other one is we can just keep it. So that's easy. If the BQ is not equal to S times BR, then this problem is infeasible. Okay, so that's a simple case. There are slightly more complex cases when let's say one of them is basically an inequality, right? So it doesn't really matter which one, but let's say this one is inequality. Then basically sometimes we can say that the problem, so we can basically discard this constraint because it is kind of consumed by this constraint, right? It is basically implied from this constraint depending on what is happening with BQ and BR. So BQ does not necessarily be equal to BR. BQ in this case is less than equal to S times BR is kind of good enough, right? So for that, and it depends. I mean, if sign of S is greater than 0 or less than 0, right? So in one case it should be less than equal to SBR, in the other case it should be greater or equal to SBR if S is less than 0, right? So that is, in those cases we can discard this constraint and we are happy. But if the signs are reversed, then and the inequality for BQ and BR are BQ is greater than SBR, and if S is greater than 0, in that case this problem is infeasible. Okay, so it's kind of simple algebra, nothing really complicated over here. And the third constraint is also kind of something similar. So the third one is like when both of them are inequalities like this. So here again, like it depends on what is the sign of S and what is happening with BQ and BR, what's their relationship. So this part is kind of known, but we don't know what is the deal with BQ and BR, right? So depending on that, sometimes it is one of them is implied, so one of them is basically dominated by the other one, or sometimes we can detect infeasibility depending on the sign of S. Okay, so mostly infeasibility happens when sign S is less than 0, right? So one of them will become greater equal to when we move both of them to the same scale, and those cases can sometimes result in infeasibility. Okay, so those details are not super important. It's very simple algebra. It's kind of trivial. The important part is how do we detect this, right? So that's rather more interesting and important part. So comparing every pairs of rows is just too expensive. Okay, so sometimes we can have very large number of rows, and comparing every pair is not a good idea. So there are two level hashing that people use for this, right? So first level hashing is that they basically look at the supports of every row, right? So I think we discussed this in part 1, AQ dot, right? So this is basically a set of all non-zero indices, right? So where all the indices where the coefficient is non-zero, right? And after this, the second level of hashing. So this goes into a function, hashing function, right? And a hash comes out, right? This is not proper hash, but some numbers come out, and that's the hash. And then the second level of hashing is they basically consider the actual coefficients, but normalized coefficient. Right, so they basically make they compute the norm of these coefficients, right? Some norm, L1 norm, L2 norm, I don't know what norm they consider, they haven't mentioned it here, but they basically divide all those coefficients so that the maximum norm is 1, and that's the thing. Like after that, they basically also sometimes change the sign. The smallest index variable should have the positive coefficient, just to make everything in the same scale, and then it goes to another hashing function, let's call it f prime, and another hash comes out. Okay, now after this, if two rows are parallel, they should belong to the same bin, right? And all we need to do is these are like basically hashes of different bin, so the bins of different hashes, right? So this is some hash, this is some other hash, this is some other hash, and if there are two constraints here, then basically they are not necessarily parallel, but we can compare them, right? If some constraint is here and some constraint is here, then they are definitely not parallel, that's guaranteed. Okay, but even in this case, right, so this part is still expensive. Like here we have to compare every pairs of rows, and that's still something that they don't do, because there are still large number of constraints that can end up in a single bin. So what they do is they basically compare only the neighbors, right? So they basically sort all the constraints lexicographically, and then compare this one with this one, this one with this one, this one with this one, and so on and so forth. Okay, so that's how they detect parallel rows. Okay, so that is parallel rows, and now we are going to talk about something called nearly parallel rows, right? So this part still holds, right? And there is another concept of something called singleton variable. Singleton variable xj. So what is this? So this is basically a variable that has a non-zero coefficient in only one constraint, right? Everywhere else this variable has coefficient 0, right? So this is called singleton variable. And what do we mean by nearly parallel rows is, now consider this kind of a constraint. Okay, so a q1 x1 plus aq c, let's say xc is let's first start with equalities, right? So this is equal to br. No, this is q, right? So we are dealing with q, and here we have a r2 x2 plus A R C X C. The C is basically set of all the variables which are not 1 and 2. Okay, and this is equal to BR. Okay, so these are the two constraints, and let's say x1 and x2 are our singleton variables. So what exactly we can do here? So here and this part still holds, right? So AQC is S times ARC, right? So C again is basically a set of 3, 4 up to n. Okay, all the variables which are not 1 and 2. Basically it's trying to say that everything that is left behind after you separate out the one part, write out the one part differently and two part differently. Okay, so what exactly we can do here? Okay, this is Q. So these are, both of them are equality, and they are not parallel, because we don't know if AQ1 is S times here first of all coefficient of x1 is 0. Right, so if AQ1 is definitely not S times AR1, and AR2 is nowhere related to whatever coefficient for x2 should be here. The coefficient for x2 is 0 here, right? So this is the issue, right? So now these are not exactly parallel, but they are nearly parallel. And what we can do is that we can still do some substitution, right? So we can basically multiply this one by -1 times 1 by S, and multiply this one by 1, and just add them together. So these parts will cancel out, XC parts, and we will have some relation. BQ and BR will not necessarily go away, but there will be some term left here, which is basically in terms of BQ and BR, and we will have some relation between x1 and x2, right? X1 equal to T, x2 plus D, this kind of type of a relationship, right? And basically we can substitute one of them with the other one and tighten the bound of other one and things like that, right? So update the bounds and everything. And this we can do like there are similar cases where we have one of them is less than equal to, or both of them are less than equal to, right? So one of them is less than equal to is again like sometimes we can strengthen the bounds of one of the variable. We can't really substitute them because both of them need to be equality for substitution, but yeah, sometimes we can strengthen the bound of one of this variable x1 or x2 based on this kind of algebra. And if both of them are inequalities like this, then it kind of depends, right? So first of all, the coefficient, objective coefficient of these two variables, that is C1 here and C2, they both need to be of the same sign, and if they are, then sometimes we can merge these two variables. Okay, so these are again like regular algebraic details. I'm not really going to go over them, but yeah, that's the idea. It doesn't really matter if sometimes if they are, whether it actually matters whether they are continuous or integer variables when we are aggregating them. So if they are integer variables, then there are some more conditions which both of them have to satisfy, and yeah, in those cases, like we can basically discard one of those constraints after after we aggregate, what they will be basically become parallel constraints, right? So yeah, so that's the thing. Like in both, when both of them are inequalities, then this BQ has to be equal to S times BR, right? If we have to aggregate those two variables. Okay, so yeah, that's about nearly parallel rows, right? So basically we can do things about these two variables which are singleton variables when we have this nearly parallel rows. And again, like the question is about how do we detect them. The idea is the same procedure, right? So we hash all these rows like this, and if we have a singleton variable, so first of all, singleton variables are very easy to detect. What you can do is before you hash them, you simply remove their coefficients, okay, and just mark those constraints that this constraint is it has a singleton variable x1, and this constraint has a singleton variable x2. So whenever you detect parallel rows after all this hashing and everything, then you can figure it out whether they are exactly parallel or they are nearly parallel, like whether this case or this case. Okay, and then you can do your algebra after that, right? So that's about parallel and nearly parallel rows, and it has some impact. It basically improves overall performance by like 3%, right? So not really a big margin, but it's still kind of kind of large if we say that those rows were actually just redundant, right? So it is basically just throwing those rows away, because these are like truly redundant rows, right? So they are not really going to halt our cut generation process as well, because if these constraints were to act as a base of one cut, then that parallel row we are basically keeping that parallel row, right? So one of them is still there in the MIP model, so the cut will still get generated, right? So this speed up is purely because we were able to solve this linear program LP relaxations faster. There is no change in the nodes, number of nodes, right? So yeah, a lot of models are affected by this. So yeah, that's parallel and nearly parallel rows. Okay, so the next thing we are going to talk about is called non-zero cancellations. Okay, so first of all, what we are going to do is we are going to divide our set of variables into 4 parts. So we'll be looking at 2 constraints at a time for this one, right? So we will divide our set of variables into 4 parts: S, T, U, and you want to guess the last one? That will be V. Okay, so our constraints are like this. Okay, so this partition is based on the 2 constraints that we are looking at. Okay, so the first constraint is AQS XS, right? So these are all the variables, coefficients of sets, variables, indices in set S, variables in set S. Then we have A Q T X T. Let's add them. Okay. Then we have A Q U X U, and we don't have anything for V for the first constraint. And all of this is equal to BQ. Right. So that's a nice little constraint. The second constraint is something like this. It's R constraint. So ARS XS plus ART XT. It doesn't have anything on U, and V part has ARV XV, and this is less than equal to BR. Okay, so first constraint has to be an equality constraint, and this constraint has to be a non-equality constraint. So what is this partition that we talked about, right? So this part is parallel, right? So the part in S has to be parallel. So in other words, we can say that here we have what do we have in the paper? We have S times AQS equal to ARS, right? So this coefficients in S are parallel, coefficients in T are common but not parallel. So these are parallel. This part is not parallel. This part is only there in the first constraint, and this part is only there in the second constraint, right? So this is how we have partitioned our variables. Now this is an equality constraint, and this is a inequality constraint, and we know that we can basically multiply this with anything and add it to this constraint, right? This is always allowed. So what happens if we multiply this one by minus S and if we add it to this one? So what happens? So first of all, S times QS, and here we are doing minus S times QS, so ARS is S times QS. So this part will cancel out. X coefficient of XS will become 0, right? This part will have something, right? Non-zero, right? So that's how do we do non-zero? We don't know how to draw non-zero, so let's draw something, right? Let's draw this. This is non-zero. This non-zero times xt. This part was not there before. Here it was 0, and so now when we multiply this by S, this part will come here. So let's draw another non-zero, right? This part times xu, and this part will not change, right? So this part was as it is, something times xv is less than equal to some coefficient, right? So some right hand side will be there. Okay, so we made some part that was non-zero in this constraint 0, and some part that was 0 here, right? Here was 0, something which is non-zero, and this non-zeros are like kind of interchanged, like they are not gone, but they are now different coefficients. This is exactly as it is, and this part has also changed. So we removed some non-zeros and we added some non-zeros. So what's our net gain in number of non-zeros, right? So we have added mod s times zeros. We basically removed this many non-zeros, and we added the mod size of u times non-zeros. That many non-zeros we added, right? So net we have removed this many number of non-zeros, right? So this entire thing is our total reduction number of non-zero cancellations, and if this is greater than 0, that means we have reduced our number of non-zeros. So if we have lesser number of non-zeros, then solving the LPs is kind of faster with simplex, right? So that's something that we all know. So that's the goal, right? We want to reduce the number of non-zeros in our matrix, and by doing this kind of adding equality to some non-equalities. So that's the basic idea what we want to do. Now, can we do this efficiently? How exactly we are going to do this? So first of all, comparing again, like every pairs of constraints is super expensive, but that's kind of one of the methods that Gurobi actually uses, right? So they basically detect all the equations. So that there are so many ways in which we can do this type of non-zero cancellations, and some of them make use of the structure, some of them don't. They all have their trade-off in terms of how effective one is, how much time it takes, and how applicable it is, and all those things, right? So the trivial thing is that we take all the equations, like equality constraints, and then try to find out all the inequality constraints which has a common support, very large common support, right? So what is the common support? Is set of S and T. So S is common, T is common, right? So wherever this part is super large in other inequalities, those inequalities we can consider, and we can try to evaluate if this will help us reduce the non-zeros, right? And again, like of course there are some special structures you can look at, either cliques or something like that, and that would even help you more, right? So that's the idea. That's the main idea. And still, like the worst case, the complexity of doing all those things is quadratic. So we have to add some sort of a work limit on this, right? Right. So we typically do not use time limits for preprocessors, because time limits are not deterministic. Wall clock is not deterministic. So we basically use this kind of work limits, like how many number of operations we perform. And if that many number of operations have been performed, then we just simply stop it. Otherwise, that will just keep going on, right? So this work limit is actually there for all preprocessors we discussed today, right? So all preprocessors that take a look at multiple constraints at a time, they all require some sort of work limit. Otherwise, they will be like basically take too long. Okay, they are not like looking at one constraint at a time. Okay, so that's the idea. And there is one more detail about this coefficient. The scale coefficient S. If this S, right, if this S is the mod of S, let's say if this is like too large, so one coefficients are like too small compared to the other coefficients, then we don't do this, because then it can, of course, like we are going to cancel this S coefficients, but when we multiply this part with minus S and this part with minus S, they will add some non-zeros here, which will have significantly different scale than what what we desire, and so that could basically lead to numerical issues, right? So that's why basically Gurobi people don't do this type of non-zero cancellations if this is the case, right? So if the size, the weight S, so absolute value of S is greater than 1000, then they just don't do it. And this is actually very impactful, right? So overall it leads to about 5% improvement. On the affected models it's 9% improvement in terms of solving time. And again, this is also not change in the nodes, it's again like the change in the time only, which basically because the LP solving is faster because we have fewer non-zeros. Okay, so this has been a pretty long video and we discussed a few things, right? So we discussed Presolve reductions that are looking at multiple constraints at a time. We talked about redundancy, right? We talked about parallel rows and nearly parallel rows, and we talked about non-zero cancellations. Right, so we discussed all these three parts in this video. And so redundancy we discussed, like it is first of all, like, you know, for MIP it's kind of very hard to detect, and not all types of redundancies are actually, you know, redundancies. Like they are redundancies, but they are not really, removing them is not really helpful all the time. So that's why most of the preprocessors about this are disabled on Gurobi, right? So we discussed about parallel rows and nearly parallel rows as well, and how to detect them, and what's the engineering things that they do to, you know, detect them, and what exactly we can do about when we detect them. And then finally we discussed about you know, non-zero cancellations, reducing the number of non-zeros in our constraint matrix, which leads to some speed up. So that's kind of all for this videos. I hope you liked it, you learned something. So hit the like button and share it with your friends and subscribe, and yeah, I'll see you in the next video. Bye.